Okay, so once you start to add your titrant, you're going to create a mixture. Okay, the mixture will make the 4 plus to become 3 plus, and this 2 plus becomes 3 plus, right? Once you add that, you're going to have this kind of thing. Think along standardization. Okay, standardization, you will know the quantity to begin with. Okay, for standardization, then your titrant, you will know the concentration as well. As you measure the burette, read the burette, you're going to add a volume. So the MV, then you know the quantity, right? Okay, for titration curve, we have just 3 regions, right? Before the endpoint, at the endpoint, and beyond the endpoint. So now let's look at the situation for before the endpoint. So before the endpoint, we know the Fe2 plus, how much to begin with, right? So before the endpoint, you're going to add your titrant. Then you will need to know how much is left, because before the endpoint, this is true. You're going to have excess quantity, right? Then what about the generated quantity of that? Then, of course, it depends on the coefficient relationship of how much of that added. So how much of that added is limiting, right? So the limiting agent is that. Okay? So what it amounts to, you will be able to get that concentration as well as this concentration, isn't it? Any question with that? On the other hand, if you look at this ratio, before the endpoint, this is a limiting agent, so the limiting agent is all used up. So you're virtually 0. Okay? But that 0 is not absolute. It depends on the x come back from your product. Okay? So that carries a small x. Well, this x can be calculated for by using the equilibrium K calculation, which I will illustrate later. Okay? Then what about how much of this is generated? Then okay, so how much of this generated then depends on the Fe2 plus, right? So how much of this generated is, when you at one end, then okay, that end, then depends on how much of that is reacted. So the reacted quantity represents the same number of moles here. Okay? So what it amounts to is that this is inconvenience to calculate, while the other 2 are more convenient to calculate. Therefore, the decision is you're going to employ the Nernst equation relating the iron for before the endpoint. Okay, any question with that? Now at the endpoint, both your titrant and your analyte is going to contribute, and I will derive the formula for this potential right here. Okay, so after the endpoint, initially you have Fe2 plus, but now all the Fe2 plus has been transformed into Fe3 plus, right? And therefore you have none left. This is your analyte. Okay, beyond the endpoint, you have none left. So virtually 0, but it's not actually absolute 0. Again, because at equilibrium, you're going to have a reverse arrow to generate back the little x. Okay, so you will have a little x. What about the 3 plus? Well, the 3 plus concentration is going to be equal to the entire quantity of the 2 plus. So initially, you have the 2 plus. So you add the serum 4 plus to change all that into 3 plus. So 1-to-1 coefficient. So when this guy change it, then itself is changed into this. Okay? So all this is going to change into 3 plus to relate to the 2 plus. Okay? So all of that is now numerically equal to that. So that's why.
The initial iron,
Right. The initial Fe2 plus concentration now is that. Okay, so beyond the endpoint, you're going to have excess of that. So you can calculate for the excess. You know the M, you know the V, so you calculate the excess quantity. So what it amounts to after the endpoint, this ratio may be determined more conveniently. Okay, so this is going to be based on the cerium Nernst equation for beyond the endpoint. Yes?
Can we always assume that when we're doing a mixture like this, that the titrant will always be the more convenient one to calculate after the endpoint? And before the endpoint would be
Right. The fact is titrant. Yeah. So what is a known concentration? So the MV, you know the number moles. Okay, so I'm going to illustrate by using an example, numerical example. Okay. Let's say 40% finished the titration. You know, this is equivalent to after adding so much of your titrant, so that 40% of your analyte reacted. Okay, 100% is at the end point. So 40% titration, so that is before the end point. Before the end point is going to be based on your analyte, right? So the potential, your analyte is the iron, E naught. Okay, the Nernst equation. So 40%, so you're going to have 40 over 60, okay, between the 2 iron species, okay? So it's 100 iron, so 40 become the 3 plus, and 60 is still left behind as 2 plus, okay? So the oxidized over reduced with the plus, okay? So with that, you can calculate the corresponding potential to be equal to that. So whatever before the endpoint, which is whatever less than 100%, your calculation will be the same. Okay, you simply just change the ratio. Okay, so instead of percent, you can calculate the concentration. Okay, so that is not a problem. Now, at the endpoint both, let's assume 2 chemicals, that each chemical has its own E naught, okay, and number of electron transfer, and the sum of the number of electron transfer. So this is your formula, and we will prove that later. For this particular titration, the E naught for cerium is this, and the E naught for iron is this. So after 2, 1 electron transfer, and therefore divided by 2. So at the end point, your potential is going to be 1.1. Okay. Then in your real titration, then you need to verify that indeed the number of moles now equal, coefficiently equal, so that it is at the end point. Okay. Now here, beyond the end point, you're going to use the titrant, right? So the Nernst equation will be this one. Okay. So the E naught, so it's 40 over 100. So it's 140, right? So So it's going to be 140 somewhere, so if 40 change, 100 over 100. Okay, so that is the potential. Now here is an interesting point. When you have 200% beyond the endpoints, then your potential is equal to the E naught, the standard potential. Okay, so keep that in mind if you want to match for some particular reasons. Then just go ahead and do 100% titration. Then you can get the E naught. So that is a way for you to realize an unknown E naught, right? You just do a 200%, so 100% beyond, then you measure the potential, then you realize, okay, this is the E naught.